Anyway, all right, guys. So, all right. So now let's start to understand vectors. Show some respect to the vectors. All right. And the first thing you want to do is call the names properly, and that's why. Yeah, Manuel. Well, so I guess that you might have your own way to deal with, that kind of stuff, right? I'm just sharing with you, right, what I found to be useful, right? Anyway, so please understand that, even if you're not a kid anymore, right? Well, even you're a kid, right? What if the teacher, what if your friend or anyone that keep calling you by the wrong name? Maybe they didn't realize, right? Maybe, and that's why, it's very stressful. Trust me that it's stressful for our teachers to read out your name because they want to do it right, but they know that sometimes it's hard for them to do it, right? So now, please call the vectors properly, right? So you come to me during the office hour, right, trying to explain to me what a vector is. You say, hey, Dr. Wang, that thing, right, with the arrows, the line stuff, right? You know what I'm talking about. I mean, yes, I do understand what you're saying, but they're not happy about, right? You're calling them like that, right? They have names, right? And that means that you're probably not going to get along with them. You don't even call them properly. So vector is, like I told you before, it is a number that has direction. But how would you show that vectors are numbers with direction? You need to show people what the direction looks like, right? By drawing an arrow, right? And since it does have number, so you want to see that sometimes the arrow might be longer or shorter, right? So what we do is we will define a vector with 2 points. It has a initial point, right? Yeah, you can call it like starting point, but in our book we call it initial point, and the final or the terminal point, and the arrow that starts from the initial points at the final or terminal point, right? And the length of the arrow tells you what that number associated with the vector, and the direction, as you can tell from the vector, it's whatever direction it's pointing at. Now, instead of calling the number of the vector, right, we say it's the magnitude of the vector. Okay, so let's say this vector is someone that move in that direction in 10 meters. That 10 meter is the length of the arrow, but we call it the magnitude of this vector. Right? But it's just terminology. But like I said, vectors, just like people, they do want to be addressed properly. Okay. So now again, these are in a book. It's probably not enough time for you to write down a lot of things. So just follow along. And again, the most important thing is, you open your minds to something that's new, may not behave the way you want them. It's just because you're not used to, a slightly different system. Okay. Now, so now you know how to call them properly. So you now better know how to spell their name or write them down properly. Okay. So vectors has names. You can call them V, W, or A, or sigma, right? Any kind of a Greek letter, beta, right? But the thing is, what if you write V and people thought it's just a number, right? So you need to let people know by either making it thick enough, like a boldface, which is very hard to do, right? When we're taking the notes, how would you make it thick enough for me to tell the difference? Well, that's just, time consuming, right? So we have a way for you to tell people, hey, this vector V has direction. So you put a little arrow on the top. It's just a way of writing the vector. Like put a little hat on it, says it's a vector. Okay, so just put an arrow, let people know, oh, that's a vector. That's how you write. But as you read the text, you see that those letters in a bold font. All right, so now remember that yesterday I was showing you those triangles with the size 3, 4, and 5. And I said that just make it properly. I'll put an arrow on the top of 3. So the arrow tells you that this is not a traditional number. But what does that number 3 represent? It doesn't have to be to the right, but you're right. It has to be 3 units long, right? So now, before I can call it a proper name, right? I haven't thought about a name, right? So the 3 is pretty much its name. It's a vector with a magnitude of 3 units, right? You can call it a vector 3, but since it's a vector, it doesn't behave just like a number 3. But what if you want people to know this is a vector that has magnitude? Let me say, what is the magnitude? We came up with a notation. If you put a vector within this kind of a double bars notation, it's almost like an enhanced version of absolute value, it returns the magnitude. So now you guys tell me how much that is. A vector with a magnitude of 3, if I get a magnitude of it, will it just be 3? Right? So do you see that? The notation, I mean, as long as you get used to it, it's pretty systematic, right? Again, so far, it's just, me telling you that that's how we write in academia. Like I said before, if we get to, figure out these things in math, maybe before those people did, then you get to actually came up with your own rules, right? But now we kind of have to, follow their rules. Okay. Now this is kind of silly to even mention it. If you see numbers, you can tell right away whether they're different or not. But when it comes to vectors, since vectors has not just only numbers, they also have directions. But it turns out that if you want to see that if the 2 vectors are exactly the same, you have to see whether they have the same exact magnitude. Or graphically, you see that they have to have the same exact length, arrows. And also they must be in the same exact directions. So they have to be perfectly lined up, right? Or parallel with the same length. But they don't have to be exactly on top of each other. You can have a vector over here and another vector all the way there. As long as, I'll try. They're pointing the same direction with the same length, they are equal. Okay. Yes. How would you write it differently? You call them differently. Because right now it's like, now remember when you see numbers like 2 and 3, are they the same? No, you see that they look different, right? But vectors, you kind of have to visualize. You see a vector that going this way, right? If you see the vector that going in a slightly different direction, they're different vectors. Maybe they look the same length, but the direction matters, right? Or look at those 2 guys. You might say, oh, they have the same length, they are parallel, right? But you know what? One going this way, the other going that way. They are completely opposite of each other. You'll see in the future, but they are still 2 different vectors. Okay? Only the ones that have the same exact direction and the same length are equal. If they ever off by a little, when it comes to direction, when it comes to the length, right? Even they're in opposite direction, but still line up, right? Perfectly parallel, but they are 2 different vectors. Okay. Now, but I don't want you to feel like that. Vectors are some kind of alien creatures that they don't have the similar systems, right? Or not to mention systems, they have completely different systems. This is like, those little kids, you thought that they don't speak your language, but turns out they do, right? Your little siblings speak English perfectly, right? But like I said, it's hard to communicate with each other since, you have your own rule, they have theirs. But let me show you something that numbers that you're so used to, right? You've been learning for the past decade. And vectors, which are another kind of numbers, right? Numbers with directions. they do share a lot of things, right? Which is good, right? Because now you don't have to learn a whole set of new rules. It's like it's never going to be a language issue for you to talk to your sibling. It's more about like a parenting or strategies, right? Now look at those two guys. Can you imagine back in elementary school or even kindergarten when they introduce you the number systems? They choose not to tell you there's a zero. Or what if our system doesn't even have a zero? Or what about one? And funny is, nowadays everything's about computer, right? Technology. Computer is all about zero and ones. So now you're telling me that the number system that we have worked out, right, for hundreds of years, right, thousands of years, doesn't have the number 0 and 1 in it, right? That's hard to imagine. Now, guess what? Vectors are the kind of numbers that they also have 0 and 1s. Yes, ones, because they are different, vectors. They're one. But 0 is only one vector that could be called a 0 vector. It is a vector has 0 length, 0 magnitude. But can you imagine a vector, which is an arrow, by the way, has 0 length? It's a point, right? So now, would it matter anymore if you talk about the direction of a point? No, right? This is probably the easiest, not the best, because you're not getting anything from it, right? But it's the easiest vector to deal with because it has no direction, right? Because it doesn't matter whether it has the direction or not, right? It's only a point. But the ones are called unit vectors. The reason why we call it unit vector is because their magnitude is unity. Unit means one, right? But a vector 1 could be going this way, that way. They are different, right? But at least that they all have the same exact magnitude, which is 1. We'll deal with them later, but at least that you know that they're just like numbers. They do have their 0 and 1s. Now, like I was saying maybe 10 minutes ago, are you guys open to see how vectors behave or communicate with each other? Oh, they are. Yeah. Well, just like, the little kids, they love to play with you guys if you're willing to play with them. Really? Yeah. But my son likes to play, if I know how to play the Minecraft or Roblox, right? The kind of things. Then yeah, he'd love to play with me. Or even sometimes try to learn the games I used to play, like a Monopoly kind of thing. The more complicated version, right? He'll try to learn and play with me, but I just don't have the time to do that. Anyway, so hope that you guys are open enough, to learn some new rules. But wait until you see those rules. And are they really that different from the ones you know? Look at the title. Properties of vector addition. So it is addition, but only for vectors. So I say that two vectors. Notice that they're both, right? Both faced. So the vectors, they add up and order doesn't matter. You know what the fancy way to call it? Commutative property. But isn't that the same thing, right? For numbers, right? They add up and 2 plus 3, 3 plus 2 are the same, right? Associative property. That means you add up the first two at the third, right? Or add up the last two at the first one. It's the same. Or zero vector. You add the 0 to anything, doesn't change, right? Or hey, what is this guy? A negative vector, right? Or a opposite vector. Can you think of a number that's opposite to 3? -3, right? How do you know -3 is going to be opposite number? How do you define opposite number in the first place? Whatever numbers added to be 0 are called opposite numbers, right? Therefore, guess what? The vector and its opposite add up to be a 0 vector. Okay? So can you imagine that if I didn't even show you the title, property of a vector addition, you thought that these are just the rules that you know back in kindergarten, right? Yes. Good. Yeah, there are. Well, just be fair enough because numbers get to have that, and vectors get to have more. right? Anyway, so now take a look at these. Scalars, but don't freak out. You know, scalars are nice numbers because they are numbers. They are the numbers that you used to know. But we used to call them scalars. So then vector, scalar. So you see, scalars are pure numbers, right? Vector is the number with directions. Okay, they do interact with each other, but they kind of have to follow the rules. Yeah. All right. All right. So let me do that quick. All right. So now again, if I didn't tell that they are called the scalar multiplication, any of these rules, just look at them. Do you find anything that you couldn't understand? What's going on? Do they just look at numbers? You distribute a number, right? Hey, 1 times u is 1. 1 times u is u. 0 times u is 0, right? So those are the rules that vectors share with the numbers. But unfortunately, that vector is going to have something that numbers don't have. Okay. But so far, I think that it's a bit too abstract, you know. But that's why, you know, people are scared of the vectors, right? There's so many things that just, you know, strange and different, right? So now let's visualize. All right, so I'm gonna turn off the light so then I have some simulation to let you observe how those vectors behave. Yes. So I'm gonna have to include that you know, simulation in today's recording, so that because I think that whoever watched the recording is gonna benefit from that. All right. All right. So now I have a vector, right, and I can have the value, which now for some reason, guys, the reason why we say that we have notations, we have this notation from our textbook. You see that people sometimes do put the absolute value, you know, instead of putting double bars. But you probably see college professors, some of them use just single bars, some of them use double bars, right? But you know, in the context that they mean by magnitude. So we have a magnitude which is 5, right, for this vector. And I can make it longer, right? Or I can make it the other way around, right? So I have a vector A, right, who's to the right with a magnitude of 10. And I have another vector, which is 5, right? So now, without me telling you anything more, just take a guess. How much they will add up to? Wait, I never give you guys trick questions, right? Did I? How come that you think that I'm always asking you those trick questions? You know, isn't that a simple?
You always do that anytime you introduce. Yes, they said 3 plus 4 is not 7, it's 5. So 10 plus 5 is not.
Okay. Oh, so I'm glad that makes you alerted that there'll be some traps. But Christopher, yeah, you have a question? No, it is 50. But does it make sense? Okay. Amaya says they're in the same direction, right? One had length 5, the other had length 10, right? They added to be length 15. But what's more is they're in the same direction. That's why they added to be the vector that in the same direction, right? Okay. Now, what if I make the vector the other way around? So now, what do you think? Okay, Grace, you said 5. In what direction? You know, the vector doesn't care about. To the right, okay? So it follows the bigger one. Okay, things has, you know, start to add up, right? Yeah, you wish that things ends at this point, right? Everyone's happy. But unfortunately, there are a lot more. But so far, you see that, I mean, it's understandable, right? They're almost like numbers. but things gets, you know, worse, you know, when you move up to a higher dimension. Now, I have a vector. I can show you the direction of it, right? The length of it, that's a 10, right? And it's pointing in a direction that makes an angle of 53.1 degree, right? But it's an arrow. And I have another one. Say, I can make it maybe a bit different. Maybe, you know what, make it 8.1. How much do you think they will add up to? 18.1? Good. You know what? Almost every single student in the physics class, if they've never taken it, or if they've never taken a vector in a you know, algebra class, they will say, how come it's not 18.1? And you know, they have, you know, they struggle with that, and after first couple weeks, and they drop the course. Right? But now you realize, first off, it's not 18.1. That's good. But if I'm asking you how much it is, it's hard to find out. But what if I tell you that I couldn't even find out right away how much they add up to unless I sit down and calculate for a minute? But you will see that there's a better way to understand how they add up instead of thinking about how much they add up to. All right, so again, let me show you the vector that they add up to. All right, so make them even worse. Okay, so now it's just, you say, well, what's going on? Am I still in the same universe? Like the math doesn't work the way I thought, right? So there's no way that 11.4 plus 13.6 is only 21.9, right? So, okay, that's their way, right? So now let's see, we need to understand how these two vectors talk to each other, right? They say, let's add up, right? But in a way that, you know, those adults don't understand, right? It's like a secret of communicating with each other. So you guys know what rise and wrong are? Okay. Now guess what? Those vectors has rise and wrongs. And a way to get them is as simple as calculating. Let's make them bigger, right? Then you can see that. Now, you guys have a calculator with you, right? Can you do me a favor for the first vector? Forget about the second one. The first one, you have an angle. Let's make this, I couldn't, you know, just whatever. So the magnitude is 21. The angle is 64.7 degrees. Can you guys calculate the horizontal and the vertical side of this right triangle? Do you guys know how to calculate these two? And convince yourself that the horizontal run is 9, the vertical rise is 19. Or SOHCAHTOA, right? So how do you get the adjacent of the angle? Hypotenuse given. Adjacent is going to be the one associated with the cosine, right? So take 21 times cosine 64.7, that's 9. You know, 21 times sine 64.7, that's 19. So you might say, you know, why am I showing the rise and run? Okay, so now turns out that those vectors, they add up in their rise and runs. Take a look. This guy has a run 5, run 13, and the sum of the two vectors has a run of 18. And the rises add up perfectly. They don't, because they act like maybe a rebelling teenager, right? But if you really understand what they're trying to communicate with you, right? And see, that's how they figured out a way to secretly add up. But you need to understand this is their rules. You know that, you know, well, of course, you know, you don't like to see something different from what you're used to, But if you say, no, you guys add up to be whatever, maybe 22.2. I don't want 21.1. It's not going to work. Just like, you tell them to do whatever, right? Don't let them even ask why. Not to mention, even if you do know why they have, to follow the rule, they might choose not to. So now the question is, would you like the magnitude of the vector and the angle, because the angle tells you the direction of the vector, or would you like their rise and rounds better? The size, right? The rise and rounds. So now, how about we don't call them rise and rounds? I use them to make sure that you guys can see it right away, but they are called components, right? Just like, our students can have many different components on their resume, right? You have the GPA, right? You have, the activities, right? You have some kind of other things, right? Vectors have their own components, and it shows how much horizontally the vector has to move, right? How much vertically they have to move. And you know that vector can go some other directions, right? So what if I have a vector that goes in that direction? So now you have a big angle, obtuse angle. Now, if you were to do the same exact algebra, taking the magnitude of the vector, multiplying cosine of whatever angle you have, which is 141.8, you're going to get a negative run. And it makes sense. Keep that negative sign because it tells you that the vector is going to the left. Right? But it has a positive run because, the sine of 141.8 degree is still positive. Okay? And yeah, that's how the vectors. Okay, let's see. It does the same thing if you follow the components or the rise and rounds. Let me show you that. You see that here we have a negative 13, right? For the rise, that means it go down. That is a positive 7 that goes up. Well, guess what? The sum of the vectors has to go down, but not as much, since negative 13 and 7 add up to be negative 6. Still, the rise and rounds add up, but let's say there are corresponding components. The horizontal components add up just like numbers. Okay, so now if you understand that, you know what, like Naya was asking, would there be any more operations? Like, would there be multiplications? Now, the good news is there's no divisions. Okay, so we do have multiplications. We have addition, subtractions. Now, if you appreciate the components, you're going to have a good time with the vectors. And those are the ones that screw up a lot of students in physics in the first 2 weeks, right? But you see that it took us almost a whole semester to get to this far, but then you realize it's still basic SOHCAHTOA. Not to mention that, do you have to remember what is sine 53.7 or sine 41.2? No, just type in a calculator. That's all, right? But there's some other things I would like to show you. Let's see what if I line these vectors in a way now remember that S is the sum, right? A and B, they add up in a vector way. So you see that numbers works out in a somewhat complicated way because you have to get the components, right, to see how they do really add up, right? But of course, there's no way that 15.8 plus 10.6 is actually 18. But let's see, how do the vectors add up in a visualized way? Let's see if I can do that. Do you see that? So it's like the two vectors add up head to tail, and the sum is just the vector that completes the triangle. And now you know why initially, if we have the vectors perfectly line up, get to that, vector 12, say, If they perfectly line up, it works out, but it is because that when sometimes they don't line up, it's some kind of a non-straightforward geometry going on. And the reason why you don't see it is because you keep thinking about the regular numbers. But you know that how to calculate the third side of a triangle if you have to add these two up, given the angles. And this is why we choose to introduce the vectors after log sine and log cosine. But I hope that you realize you don't have to do that. If you can ever find out the components or rise and runs, and they will add up perfectly. Okay. But so far, we are facing what they call a dilemma. We know that those vectors add up in components, but we're not given components. You know that in the test, we're going to give you the magnitude and angle. And you have to stop yourself from thinking about the magnitude add up, because they don't. You have to get the components, right? So we have a way for you to write the vectors in a nicer way so they're ready to be add up, just like numbers. So now let's go back to the notes. Right. So we have something called the unit vector, the same kind of unit vector I was talking about, but there are two very special unit vectors, and they're called I and j. Again, don't ask me why they call it I and j. So I don't know. So they choose to just maybe IJK. Well, you know what? Because there are only so many letters in the alphabet, right? They have XYZ saved for something else, ABC, right? M and N, right? So I and j somehow left over. M&Ms. No, well, they're usually integers. So I and j are so special because they must be lined up with either x and y axes. So I is a perfect horizontal unit vector, and it has to be always going to the right. And the j is a perfectly vertical vector that has to always go up. Now, how do I utilize the I and the j? So again, I can tell that you guys like rise and run, right? So what if I tell you that I can make the rise and run right in front of you whenever you have to write the vectors, so that you can even think in mental math, right, how they add up. But you have to take the functions for I and j. Say this vector, if you figured out what the rise and the run will be, put the rise, keep saying the rise because rise goes first, put the run in front of the I. It's like I times, or A times the I, which is the horizontal run, let's say however many units, right, times the I. That means you're going to make that many steps to the right. Then the J tells you you're going to move up for how many steps? B. That's the rise. Okay, so now let's see if it works out maybe visually. So I'm going to go back to the simulation. All right, so I have, so let's make the A. Now, of course, you can call it anything, but they choose to call it, J and K. But if you don't mind, can you pretend that, as if that A is I, right? It's a horizontal unit vector, right? Pointing to the right. And let's make the vector B the so-called unit vector J. Okay. So this small, of course, right? But they are the two unit vectors, right? That perfectly lines up with the x and y. So now I have a vector C. The vector C is made of a certain number times of A, which is, remember, it's I, right? And a certain number times of B. So let's say right now, the number in front of A is how many units of the run you must have. And the number in front of B is how many numbers the rise, right, you want. And let them, add them up. The C does have exactly 1 unit of run to the right and 1 unit of rise to the, going up. Okay, so now what if increase the run? So now do you see that the number in front of A tells you that you're going to go to the right by 5 steps, right, in that direction. So C has 5 units of run, right? So now if I increase, the number in front of B. But what is the C? Let me show you. Oops. It does have exactly the number rise and run you want. Is you just breaking it up instead of calling it a vector of magnitude of 7.1 angle 45 degree, you say a vector of 5i. Sorry, I see that you have an a there, right? 5i plus 5j. If you write it like that, everyone's going to understand, oh, you're talking about a vector like that, has 7 units run, 10 units of rise. Can you picture that in your head? A vector that goes to the right and going up, right? So now check this out. What if I'm asking you to do a vector addition? Oh, where is it? So the vectors have different rise and runs. And guess what? You add them up, you group the like terms, they're all going to have certain amount of rise and the runs, right, associated with I and J, and they add up just like we would expect.